This chapter, I am going to cover these examples from sections 1, 2, and 3. And then I'll also cover some problems from the review at the end of the chapter as well. So I would recommend that you use these problems as a guide to help you practice for the homeworks and to study for those quizzes and the midterm exam. Okay, so for the first problem that we're going to look at, that is here on section 1.1 in your textbook. And this problem is asking us to state the order of the given ordinary differential equation and then determine whether it's linear or nonlinear. And so in this case, what we can see here is that when we have this second derivative here, that tells us that this is second order. Okay, so it's a second order derivative or a differential equation. And then this portion right here, where we have this cosine of r plus u, this right here shows us that it is nonlinear. Okay, so this is a second order differential equation and it is nonlinear. Okay, for this next problem, again, out of section 1.1, so this is like problems 11 through 14, and you're asked to verify the indicated function, that the indicated function is an explicit solution of the given differential equation. Okay, and so for this one, the first thing we want to do is we're given an equation here, our y equals equation. So the first thing we want to do here is determine our first and second derivatives, because we're going to need the second derivative to do this verification. And so we have dy dx of our function. So that's cosine of x ln of the secant x plus the tangent of x. Okay. And so remember, we can pull this negative here to the outside just to help make things a little bit easier for us as we do these derivatives. Just another reminder, we have that when we want to take the derivative of the product of two functions, that is just our f prime g plus our gf g prime f. Okay, and so the first thing, if we want to look at this, our f function, that's going to be just our cosine of x, and our g function is going to be that ln of the secant of x plus the tangent of x. Okay, so when we take the derivative of each of those, our f prime, the derivative of cosine is negative sine of x. And the derivative of our ln secant x plus tangent x is going to just be our secant of x. Okay, so when we put that all together with our for our y prime, that is going to give us, we'll keep that negative on the outside, right? And then f prime is negative sine of x. G is that ln secant of x plus the tangent of x. And then plus our g prime, which is the secant of x, times f, which is the cosine of x. Okay. Now let's just simplify and clean this up a little bit. So we have negative 1 minus ln secant of x plus tangent of x times our sine of x. Okay. And lastly, we can distribute that negative. So we end up with negative 1 plus I'm going to just move the sign in front of our ln. So that's sine of x ln of our secant x plus tangent of x. Okay. So now that we have our first derivative, we can use that to calculate our second derivative. So that's going to give me my y double prime. Again, we can use that f prime of g plus g prime of f. Okay. And so my f function here is going to be the sine of x, and my g function is going to be that ln secant of x plus the tangent of x. So when I take the derivative of each of those, so the derivative of sine of x is going to give me the cosine of x, and g prime is going to give me the secant of x. So when I put that together and to do my second derivative, then I have cosine of x ln secant of x plus the tangent of x plus the secant of x times sine of x. Remember, secant is 1 over cosine. So that would give me 1 over cosine times sine, which is sine over cosine, which is the same as tangent. So we can simplify that a little bit. So we have our cosine of x ln secant x plus tangent of x plus our tangent of x. Okay. And so if you go ahead and put that back to our original, remember we wanted to show that y double prime plus y is equal to the tangent of x. So when I take my original equation up here, right, and I add it to my second derivative down here, you'll see that I have in my second derivative, I have cosine x ln secant x plus tangent, but in my original y, it's negative. So when I have a positive and a negative and I'm adding them together, those will cancel out with me, and it'll leave me just with this term here, tangent of x. Therefore, we have shown that or verified that the indicated function is an explicit solution to that given differential equation. Okay. All right. The next problem I'm going to work out of this section is problem number 16. It's very similar to 15 through 18. We want to verify that the indicated function is an explicit solution of the given first order differential equation. Okay. And so in this case, I do want to give you guys a couple of reminders. Okay. Just that the derivative of the tangent of x, remember that is our secant squared of x, and secant squared of x is the same as 1 plus the tangent squared of x. Okay, so we might need those in part of our solution. Okay, so the tangent of x is not defined for x equals pi over 2 or any multiple of pi, right? So the domain of our function here, we're given the domain. So we're going to look at the domain of 5 tangent 5x. We have to look at that, right? And so the domain is going to be x can be any form of 5x, but it cannot be a multiple of pi over 2 plus n pi. Okay. Or if we wanted to just have it in terms of x and not that 5x, right? We could also say that it is x cannot be pi over 10 because all we're doing is dividing both sides of this equation here by that 5. And so we're getting x by itself. That means that pi can't, we can't have pi over 10 plus n pi over 5 as part of our domain either. Okay. So now we need to look at, we're given here, we're given our y prime, but let's go ahead and plug y into that, right? So we have that y prime is equal to 25 plus y squared, right? But we can just plug in our y here, which is 5 tangent of 5x, and that's squared, okay? Because that's all we're doing is plugging that in. And so this actually gives me 25 plus 5 squared is 25 plus tangent of 5, tangent squared of 5x. Okay. And so we can factor a 25 out of both of those terms. So we have 25. It leaves me with 1 in the first term and tangent squared of 5x in the second term. Okay. And so now we can see that what we have here then is that this does in fact give us an interval for this definition, right? And so we could say when we have y prime equals, we could say then that we could have also said that y prime is equal to 25 secant squared of 5x, right? Because when we're looking at our derivative, that is one of the other ways that we could have looked at that. And if we looked at it in those terms, we also know that 25 times, remember that 1 plus our tangent squared of x, but we're going to have a 5x because that's what we have is our multiplier. And when we multiply that out, we end up with 25 plus 25 tangent squared of 5x. And this really right here, again, happens to be, this is our y squared. And so we can actually simplify that to 25 plus y squared. So in a sense, we have shown here that we have an interval of definition for this solution, and that is going to be this negative pi over 10, pi over 10. And it could also be pi over 10, 3 pi over 10, and so on. Okay. Another problem from section 1.1. This one is similar to problems 21 through 24. I'll work number 22 here for you tonight. And we're looking to verify that the indicated family of functions is a solution of the given differential equation. Okay. So let's start out by determining what is our derivative. So we have y prime is equal to 4x plus 0 minus 4x C1 e to the negative 2x squared. So really, we just took the derivative of this portion of the equation here. Let's go ahead and simplify that, getting rid of the 0 that we have there. So this is 4x minus 4x C1 e to the negative 2x squared. Okay, so now we want to show that our derivative plus 4xy is equal to that 8x cubed. Okay, so now we're going to show that y prime plus 4xy equals 8x cubed. Okay, so our y prime, we calculated that. That is 4x minus 4x C1 e to the negative 2x squared plus 4x. We know what y is, so we could substitute that in. That is 2x squared minus 1 plus C1 e to the negative 2x squared. Okay, and we want to show that when we simplify this, it is equal to 8x cubed. Okay, so let's go ahead and just distribute this 4x to each of these terms. So this gives me 4x minus 4x C1 e to the negative 2x squared plus 8x cubed minus 4C 1, let's see, minus 4x, sorry, not 4C1, 4x. We're distributing it to each of these terms, plus 4x C1 e negative 2x squared. Okay, so let's simplify as much as we can. We have a positive 4x and a negative 4x, so those will cancel with each other. We also have this negative 4x C1 e to the negative 2x squared and a positive 1. And so that leaves me with 8x cubed. So now I have shown that, or verified that this is indeed an indicated family of functions, which the solution is this 8x cubed. Okay, this next problem, again, section 1.1. It's similar to problems 31 through 34. And you're asked to find values of m so that the function y equals e to the mx is a solution of the given differential equation. Okay, so it tells us that in the problem that y equals e to the mx. So if I take the derivative of that, y prime is equal to, remember, e to the x, the derivative of e to x is itself, e to the x, but in this case, we have the m in front of it. So it becomes m e to the mx. And then when we take the second derivative of that, this becomes m squared e to the mx. And we do that because this differential equation has both the first derivative and the second derivative, so we're going to do both of those calculations. All right, so now let's just plug in those into that problem number 34. So we have 2 times my second derivative, which was m squared e to the mx, plus 7 times my first derivative, which is m times e to the mx. And we want to minus 4 times y, which is just e to the mx. Okay, and that is equal to 0. Okay, so let's simplify. So this becomes 2m squared e to the mx plus 7m e to the mx minus 4e to the mx. and that is still equal to 0. Okay, we can actually factor. We could see that we have an e to the mx in all three terms. So we can actually factor that out of each of these portions. So we have e to the mx. We factor that out. We're left with 2m squared plus 7m minus 4. And that is equal to 0. We can take that a step further and we can factor, it's just the same as if I had 2x squared plus 7x minus 4. I could factor that to get 2m minus 1m plus 4 still equals to 0. And since e times e raised to the mx, these, let me make those up a little higher. E raised to the mx, they're all, anytime you raise e to something, it's going to be greater than 0. So I'll just write that little note over here at the side, right? E to the mx is always going to be greater than 0 for all of our x's. So either our 2m minus 1 has to equal 0, or our m plus 4 has to equal 0. And so if this is the case, then m is equal to 1/2. And if this is the case, m would equal -4. Okay. So our solutions here would be y equals e to the -4x and y equals e to the x over 2. You could have wrote 1/2 x, or you could write x over 2, but both of these are solutions. Okay. All right, let's move to the next section. Now we're going to look at section 1.2. In this case, we're going to look, this is similar to problems 11 through 14. And we're given a y equation, and it's a 2-parameter family of solutions of this second order differential equation. And we want to find the solution of the second order IVP consisting of this differential equation and the given initial conditions. Okay, so we're first given that our y is equal to this c1 e to the x plus c2 e to the -x. So what would our derivative of that be? The derivative is going to just be c1 e to the x, right? Because the derivative of e to the x is e to the x. This one will be a little bit different because it's e to the -x. So the derivative here is going to be minus c2 e to the -x. Okay. So from our initial conditions, right? Let's put initial conditions. From our initial conditions, we have that y1 is equal to 0. Therefore, we can plug that in and we get c1 e to the 1, right? We're substituting in the value of 1 for our x's, plus c2 e to the -1 because we have that negative in front of our x, and that is equal to 0. When we plug it into our derivative, remember our initial condition here is that our derivative evaluated at 1 is equal to e. So when we plug that in, we get c1 e to the 1 minus c2 e to the -1 is equal to 0. If we add these two equations together, right? If you think back to algebra days when we can combine those two together, it's not 0, sorry, it is equal to e here. So when we plug those in and we add them together, we actually end up with 2c1e to the 1. I'm not going to write the 1 there, right? And it is equal to e. So we can divide both sides by 2e. Okay. When we divide both sides by 2e, I am left with C1 is equal to 1 over 2. Okay, so we can substitute that back into our equation. I'll write that here. Okay, so we'll substitute that back into our equation. So we have 1/2 e plus C2 e to the negative 1 equals 0. We can minus 1/2 e from both sides. Okay. When we minus 1/2 e from both sides, we are left with C2 e to the negative 1 is equal to negative 1/2 e. Okay. Now we can divide both sides by e to the negative 1 because our ultimate goal is to get C2 by itself. Okay. And just as a reminder, anytime we're dealing with exponents, thinking back to algebra days, if I want to move this up into the numerator, all I have to do is change the sign. So this is the same as, so if I want to move this up, it's the same as moving up here, 1 to e to the positive 1, okay? And so if I had e to the 1 times e to the 1, remember I can just add those exponents together. And this is going to give me C2 is equal to negative 1/2 e squared. Okay. So let's plug that back up into our original y equation. So we have y is equal to 1/2 e to the x plus, not plus, sorry, minus 1/2 e squared e to the negative x, okay? And again, as a refresher, anytime you're adding if you have a multiplication of exponents and I'm adding them together, let me just give you guys a little tutorial here on the side. So if I had e to the 3 and e to the 2, that's the same as e to the 3 plus 2, which is e to the 5. Okay. Similarly, for this other one, I actually have e to the 2 in one, and I have e to the negative x in the other. So that's really the same as e to the 2 plus negative x. So just x2 minus x. Okay. And so that's why we can rewrite this as 1/2 e to the x minus 1/2 e to the 2 minus. Okay. This next problem is also out of section 2, and we're going to look at, it could be similar to problem 17 to 24. The one we're going to look at is number 22. So the first thing I want to do is let's find our derivative. So this is y prime. And so the derivative here of this is going to give me, all I'm going to do here is we're going to move this portion of the equation to the right-hand side so that we have that y prime by itself. And so that equals x squared over 1 plus y cubed. Okay. And so in true form with this problem, we're going to be looking at our x naught, y naught. So we can actually just write this here as our f of x, y. And that is our x squared 1 plus y cubed. Okay. And so we're looking here at these partial differential equations. And so what we have on this here is going to be our x squared, our partial differential equation with respect to y. So that is the 1 over 1 plus y cubed, right? Because we're only looking at this in terms with respect to our y. So that's why we're taking this kind of and we're pulling it to the out, right? And so that's why we have the x isolated and we're only taking that partial differential equation with respect to our y. Okay. So this is going to give me then x squared, our partial differential equation with respect to y. And so that is going to, I'm just going to bring this up into the denominator so that we don't have to use the quotient rule. We can bring it up into the denominator and we'll be able to use our chain rule to get our derivative here, okay? So using the chain rule, it gives us that we have our x squared times negative 1 over 1 plus y cubed squared times 3y squared. Okay? So essentially, we can simplify this a little bit to give us negative 3x squared y squared over 1 plus y cubed squared. Okay, so that means our partial differential equation with respect to y is going to be negative 3x squared y squared over 1 plus, clean that up, 1 plus y cubed squared. So this differential equation will have a unique solution in any region where y is not equal to 1, because that would then make that undefined. Okay. All right, let's look at the next problem. The next problem is also coming out of section 2. It's similar to problems 39 through 44. And you are, again, given a 2-parameter family of solutions of a second order differential equation. And if it's possible, we want to find the solution that satisfies the given side condition. We're going to look at problem number 42. The first thing we want to do is let's determine what our derivative of our y function is. And so that is going to be negative 2 c1 sine of 2x plus c2 or 2c2 cosine of 2x. Then when we look at our second derivative, that's going to be negative 4c1 cosine of 2x minus 4c2 sine of 2x. Okay, so we were given 2 initial conditions. The first one was y0 equals to 1. So we have 1 equals c1 cosine, our original equation up here. So c1 cosine 2 times 0 plus c2 sine of 2 times 0. So this gives me 1 equals c1 times 1, because the cosine of 0 is 1, plus c2, and the sine of 0 is 0. So that tells me here then that c1 is equal to 1. We can do the same sort of thing for our derivative initial condition that was given. We're given that y prime equals pi, y prime of pi is equal to 5. So 5 is equal to negative 2 C1 sine of 2 times pi plus 2C2 cosine of 2 times pi. So this gives me 5 equals negative 2C1 times 0 plus 2C2 of 1, because the sine of 2 pi is 0, the cosine of 2 pi is 1. And so we could solve this to get that C2 is equal to 5/2. So in this case, our boundary, excuse me, our boundary value problem solution is y equals cosine of 2x plus 5/2 sine of 2x. All right, now let's look at another problem in section 2. This time, this problem is similar to 45 and 46, and it asks us to use part of exercise 1.1. So I'll just give you that information, and then also equations 2 and 3 in the textbook. So it wants us to find a function whose second derivative is equal to the one given here at each point x and y on its graph, and y is equal to negative x plus 5 is tangent to the graph of the points corresponding to x equal to 1. So the first thing we want to do here is we want to integrate this y double prime equals 12x minus 2, right? So y prime is equal to the integral of 12x minus 2 dx, right? So for this first problem, just it's our first integration. So as a quick little refresher, when we're integrating, that's really just 12x to the 1, we're adding 1, and then since the exponent was 1, we're also adding 1 on the denominator, minus 2x, and don't forget we have to add that constant out there, and we'll just call it C1. Okay, when we simplify this, we end up with 12 divided by 2 is 6, x squared minus 2x plus C1. So now we want to integrate that, right? So we integrate our y prime, which is, we calculated at that 6, I won't rewrite it, but it's the 6x squared minus 2x plus C1. So when we integrate that, we get y equals the integral of 6x squared minus 2x plus C1. Okay, and then we have that dx. So when we take that integration here for that, we end up getting, so we get 6x squared plus the 1 over 2 plus 1 minus 2x to the 1 plus 1 over 1 plus 1 plus we have that C1x plus now we need to add out our second constant out there. When we simplify this, 6 divided by 3 equals 2x cubed minus x squared plus C1 x plus C2, okay? And so when we look at this at x equal 1, so when we look at this at x equal to 1, we get that y is equal to -1 plus 5, which equals 4, okay? So that means that y evaluated at 1 is equal to 4. So the tangent line slope at x equal to 1 is going to be y. So we would have, let me just put tangent line slope at x equal to 1 is going to be that y prime of 1 equal to -1. Okay, so we can take 2 minus 1 plus C1 plus C2 is equal to 4, right? Or we can simplify that, and that's really just C1 plus C2 is equal to 4 minus 2 plus 1, which is 3. And that is, we're coming at this from our y equation. We also have that 6 minus 2 plus C1 equals -1, or we could simplify that to C1 equals -5, and that's coming from our y prime equation, okay? Thus, we can say that since C1 equals -5, C2 is going to equal 8, right? So we could just plug that -5 up in for C1, add it to both sides, and we'll get that C2 is equal to 8. So that gives us C1, we already knew C1 was equal to -5, but we could solve by plugging this C1 up into our equation here and getting that C2 is equal to 8. Okay, so when we put that all in one equation, we get that y is equal to 2x cubed minus x squared minus 5x plus 8. So this next problem is going to, I'm going to use multiple different colors to kind of help us see how we draw different numbers, where we're drawing them from this word problem. But essentially, this is one of those large mixing tanks, and we need to do some work. And so if you remember in the textbook, you're given the function for our inflow versus our outflow, right? So N is the concentration of salt in the inflow times the input rate of the brine, and that equals the input rate of salt. Similarly, R sub out, right? The amount that's coming out, that is the concentration of salt in our outflow times our output rate of brine, and that's equal to our output rate of salt. Okay. So our R sub N is equal to, so the first one, that is our concentration of salt inflow. And so pumped into the tank at a rate of 3 gallons per minute. So that is 3 gallons per minute. We then have, for our input rate of the brine, that is coming in, it is a concentration of the solution entering at 2 pounds per gallon. So that is 2 pounds per gallon. Okay. And so that is, our gallons will cancel with each other, and that leaves me with 6 pounds per minute. That is my input rate. Okay. And since the solution is pumped out at a slower rate, it's accumulating at a rate of 3 minus 2. So it's accumulating at a rate of 3 minus 2 gallons per minute, which simplifies to 1 gallon per minute. Okay. And so after the tank, after T minutes, there are going to be, so after T minutes, there are well, we started out with 300 gallons of water. So after T minutes, it had 300 to start with, plus we need to add some number of T gallons per minute. And that happens to be just the value of 1 because that is what we calculated in the previous step, that accumulation, right? So after T minutes, there are 300 plus 1 times T gallons of brine in the tank. I'll go ahead and write that, gallons of brine in the tank. Okay. And so the rate at which the salt is leaving, that's going to be our R out, right? And remember, our R out is going to be the concentration of salt in the outflow. And so this tells me this is pumped out at a slower rate of 2 gallons per minute. So this is 2 gallons per minute times. Now, this is our output rate of brine. And so this is going to be A over something pounds per gallon. And so that is actually going to be, that's not differentiable enough. Let's do this yellow. I don't like that. Let's do orange. So that is, don't forget the T on that. 300 plus T gallons. Okay, so we have that. And when we simplify this problem, we end up with 2A over 300 plus T pounds per minute, because our gallons will cancel with one another. Okay. So that leaves me with the differential equation then of, with respect to time, as 6 from the previous equation minus 2 alpha over 300 plus T. Okay. So for this next problem, number 16, it's coming out of section 1.3. And we're going to look at a series circuit, and it contains resistors and capacitor as shown in this figure here. And we want to determine a differential equation for the charge of the capacitor if the resistor is R, the capacitance is C, and the impressed voltage is E of T. This right here is just a copy and paste from your textbook. I just took a screenshot of it so I could share it here, mostly because so you can see, the inductor. It gives us what our equations are, our resistor, and our capacitor. So when you're looking at these in this problem, that is, we have all 3 of them, right? But the problem that we are given here, we have a resistor and we have the capacitor. We don't have the inductor, right? So we don't really need this piece for the problem that we're working here, but you may come across those elsewhere, okay? And so by Kirchhoff's law, second law, E of t on a closed loop must equal the sum of voltage drops in the loop. Okay. So for this one, we have our resistor R. Okay. And that is, we have IR, which, right, IR here. But if you go back in the text and such, it's also the same as saying R to the dq of dt. Okay. Also, our capacitor, right? The capacitor C is 1 over CQ. And I'll put here, we're not going to use this, but remember the inductor, and it's also in the text, is going to be our L di dt, which is L second derivative dq of dt squared. Okay. And so for this problem, it's really just saying, remember that our voltage has to equal, it's going to be our resistor, because we have a resistor, which in this case is just our R dq dt, plus our capacitor, which is 1 over CQ. Okay. Next problem that we're going to look at, also from section 1.3. This is like number 26, but it actually references problem number 25. So I will tell you that in problem 25, and you guys can work on it, solve it, the odd problems, you can find solutions in the textbook, but the differential equation is going to be K times M minus A. Okay. So for this problem, we want to assume problem 25, in problem 25, assume that the rate of material is forgotten, is proportional to the amount of memorized in time t greater than 0. We want to determine this differential equation. And so this one now becomes a two-part. So in this problem, the differential equation is going to be dA of dt is equal to, we'll have K1 of our M minus A minus K2 of A. Okay. All right, so that takes us to the couple of examples I have in the review section. So these could come from sections 1, 2, or 3 from the coursework, but just to get a little bit more practice and a variety of types of problems. Again, remember, these are going to be problems that you will probably find helpful on those handwritten quizzes, the exam, etc. So it's really important that you probably spend some time making sure that you're familiar with these type of problems moving forward. Okay. So in the review, this kind of coincides with problems 5 and 6. And we want to compute y prime and y double prime, and then combine those derivatives with our y equation here, and to get the solution to what is that differential equation. Okay. So first of all, let's go ahead and look at our first equation here. So we want to find, we have our equation here. So we have f and g, right? So if my f function is c1 e to the x, actually it's going to be f and g. And we'll use the product rule for that. And so the second one is the cosine of x. So that gives me f prime is equal to c1 e to the x, and g prime is equal to negative sine of x. Okay, so when I look at f prime g plus g prime of f, that gives me c1 e to the x cosine of x minus sine of x c1 e to the x. Okay. That is just the first half, right? So we also need to do here, instead of calling it f and g again, I'm just going to continue with j and k. So j would be my c2 e to the x, and my k would be sine of x. It doesn't really matter what we call these. We could have called all four of them f, all four of them g. It's just a little more confusing. So that's why I went with j and k. So we have j prime and k prime that we still need to determine. Our j prime is going to be c2 e to the x, and our k prime is going to just be the cosine of x. So when I combined j prime plus times k plus k prime times j, that gives me c2 e to the x sine x plus cosine x c2 e to the x. Now let's combine it all together for our y prime. And so this is really going to just be my f prime g plus g prime f plus, let me make that not capital, plus j prime k plus k prime j. Okay. I'm going to just copy these here over. So we're going to copy this and paste it. That is my f prime g plus g prime f. Do the same for our j k prime k plus k prime j. Okay, so we add those two together. And so similarly, I'm not going to write out all of the F, J, K, etc. I have full confidence after getting through Calculus 3 that you guys can do that. So I'm just going to write what our y double prime is here. Negative c1 e to the x cosine of x minus c1 e to the x sine of x. I'm going to just shift this over a little bit to make sure we have enough room. Minus c1 e to the x sine x plus c1 e to the x cosine x. Okay. But that just is the first half. So that is just the blue one. So we have to keep going. We're going to minus off minus c2 e to the x sine of x plus c2 e to the x cosine of x plus c2 e to the x cosine of x plus c2 e to the x sine of x. Okay. So we have a negative and a positive. So those two will cancel out with each other. And then we also have the negative and the positive here, which cancel out with each other. And so we are left with negative 2c1 e to the x sine of x plus 2c2 e to the x cosine of x. Okay. So that gives us that we have our y double prime minus 2y prime is equal to negative 2c1 e to the x cosine of x minus 2c2 e to the x sine x. And that simplifies to a negative 2y. Okay. I mean, not simplify, so we still have our, yeah. And then finally, we'll have our y double prime minus 2y prime, right? We can bring this over to the other side. And so that is plus 2y is equal to 0. And that is what we were being asked to show, is to give that linear second order differential equation. Okay. For this next problem, again, it's out of the chapter review. It looks like problems 7 through 12, and we want to match each of the given differential equations with one or more of the solutions here. We're going to look at problem number 10. So when we take x dy dx, and that equals our y, really all I've done here is instead of saying y prime, I just put the dy dx, right? And we are going to integrate. So we have dy y. So all we're doing in this case is we're going to move this to this side, and we're going to move these to that side, right? So we want to get our y and dy on the same side and our x and dx on the same side. So that gives me dy over y is equal to 1 over x dx. Okay. We want to do our integration here. So we're going to take the derivative, the integral of both sides. And we have that the ln of y is equal to ln of x plus ln of c. So our ln of y is equal to ln of c times x. We're just combining these here by using laws of our rules of properties of logarithms. So we get that y equals cx, okay, where c is an arbitrary constant. So we could say that y equals x is one solution. Doesn't mean it's all solutions, but it is one solution, okay? And so now we just want to test each of those, these other equations that we were given up here, right? So if we have y equal to 0, then that is y prime equals 0. So xy prime equals y, okay? That was then that x times 0 equals 0, which it does. 0 equals 0. So y equals 0 is a solution. Okay. But it didn't say there was only one. There could be more than one. So we actually have to test all 4 of them. So if we had y equal to 2, we go through the same process. We have y prime equals 0. So x y prime equals y. So that gives me x times 2 equals 0. We're testing that. And so that gives me 0 equals 2. Therefore, that is false, right? So this one was true. So that's why it was a solution. This one is false. So y equals 2 is not a solution. Okay. Looking at y equals 2x, that's our part C here. Y equal to 2x, testing that, we have y prime. So the derivative of that is 2, right? So we have xy prime equals y. Let's put in what we know. That is x times 2 equals 2x. Well, that does simplify 2x equals 2x. That is true. Therefore, y equals 2x is one solution. Okay. Finally, we have y equals 2x squared. So our derivative of that is going to be 4x. So we have xy prime equals y. That gives me 4 times 4x equals 2x squared. So I have, sorry, this is not a 4 out here. This is an x. X times 4x is 4x squared equals 2x squared. That is false statement. So y equals 2x squared is not a solution. Okay. The last example I have from chapter 1 to share with you all is also from the review. And this one is like problems 35 through 38. I'll work number 38 here. We want to find a solution of the second order IVP consisting of this differential equation given this initial, right? So we have y prime is equal to, we're just taking the derivative of this equation that we're given up here in the instructions. And so our derivative is 3c1 e to the 3x minus c2 e to the negative x minus 2. Let's go ahead and evaluate that for our initial condition here, y prime of -1. But let's do it for both. We'll do it for the y and the y prime. So y equal -1 is equal to 0. But let's put in what our equation is. That is c1 e to the 3x, but our x here in this case is -1 plus c2 e -1 minus 2 to the -1 is equal to 0. That simplifies to c1 e to the -3 plus c2 e to the 1 plus 2 is equal to 0. Let's do the same for our derivative. So we have y prime of -1 equals 1. So let's plug that into our derivative equation here. And that's going to give me 3 c1 e to the 3 times -1 minus c2 e to the negative, let's put it in proper parentheses, -1 minus 2, and that is equal to 1. So when we simplify that, we get 3c1 e to the -3 minus c2 e minus 2 equals 1. So now we can combine these two equations. Let's just bring them down here. I'm gonna bring a copy of it. Let's copy, paste. And I want to cut it. Okay. When we add them together, okay, these cancel out with each other. The +2 and the -2 cancel out with each other. And we are left with 4c1 e to the -3 is equal to 1. Okay. And so that gives me that C1 is equal to 1 over 4 to the e to the -3, which is, remember, we can make that e to the -3 a positive by bringing it up into the denominator, into the numerator. And so that's the same as saying e cubed over 4. Okay, so let's bring our original equation piece down again. And so when we have that and we want to plug our e to the e cubed over 4 in for our C1, that gives us e cubed over 4. We have e to the -3. We have plus C2 e to the 1 plus 2 is equal to 0. Let's simplify that a little further. The e cubed times e to the -3, those cancel out because 3 minus 3 is 0. So that leaves me with 1/4 plus C2e plus 2 is equal to 0. Therefore, C2 is equal to -9 over 4e, which is the same as -9 over 4e to the -1, just bringing that e up into our numerator. And so we could write that equation as y equals e cubed over 4. Let me write that a little cleaner. E 3x minus 9 over 4 e to the -1 e to the -x minus 2x. And we can, let me see if I can move this stuff up just a little bit to buy us a little more room here at the bottom to write one more time for simplification. We have y equals 1/4 e to the 3x plus 3 minus 9/4 e to the -x minus 1 minus 2x for our final solution. These up just a little bit to get us a little bit more room.